All right, let's talk about something that trips up a lot of people. Vector triple products. You see three vectors in an equation and your brain just kind of freezes, right? Like, what am I even supposed to do with that? Well, you're not alone. They look super intimidating, but I promise, by the end of this, we're going to pull back the curtain and make it all make sense. So let's get right into it. Multiplying two vectors, no problem. You know the dot product, you know the cross product, that's old news. But what happens when a third vector crashes the party? All of a sudden, you've got these expressions like A dot B cross C or A cross B cross C, and you're thinking, what is this mess? But here's the cool part, they aren't messy at all. They're actually describing some really elegant and honestly really useful geometry. And that's really the big secret here. Those parentheses, they're not just there for show. They are your roadmap. They tell you exactly which step to take first, and they unlock two of the most powerful tools you can have in vector algebra. Seriously, by the time we're done here, you're not going to see these as scary problems anymore. You're going to see them as awesome shortcuts for figuring out things like volumes and planes. Okay, first up, let's tackle the scalar triple product. And look, before we even think about formulas, I want you to lock this one idea in your head. Its job, its whole purpose in life, is to find the volume of a 3D shape, a shape made by three vectors. That's it. It's a volume tool. So let's build this thing from the ground up. Picture a flat surface, a plane. Now let's draw two vectors on it. We'll call them B and C, both starting from the exact same spot. See how they naturally form the sides of a parallelogram? I want you to think of that parallelogram as the foundation of our shape, like the concrete slab or the floor plan of a house. All right, so we've got our floor plan. How do we describe it using math? Easy. We use the cross product. When you take B cross C, you get a brand new vector. And this new vector is pretty special. It has two killer properties. First, its length, its magnitude, is the exact area of that parallelogram base. And second, its direction, it's pointing straight up, perfectly perpendicular to that base, all thanks to our old friend, the right-hand rule. Okay, foundation's poured, area is calculated. Now let's bring in our third vector, vector A. This is what gives our flat shape some height. It's like it grabs that 2D parallelogram and pulls it up into the third dimension, creating this kind of slanted box shape. And that shape has a name, a parallelepiped. Now you can see it, right? Vectors A, B, and C are the three main edges of this solid object. And this right here, this is the whole idea behind the scalar triple product. That formula, A dot B cross C, it's not just a bunch of symbols. It's a set of instructions for finding the volume of that shape we just built. Think about it. You take the area of the base, that's the B cross C part, and then you're dotting it with A. That dot product is basically asking, hey, how much of our height vector A is actually pointing straight up, perpendicular to the base? The answer isn't another vector, it's just a number, a scalar. And that number is your volume. So how do you actually calculate this thing? Well, the good news is it's surprisingly simple. You just take the components of your three vectors, A, B, and C, and you stack them up as rows in a 3x3 matrix. Then you just find the determinant of that matrix. That single number that pops out, that's your volume. It's a super neat and compact way to get the job done. Okay, so that was the scalar triple product. Its job is volume. Got it. Now, let's switch gears and talk about its cousin, the vector triple product. And it has a totally different job. If the scalar product was our volume tool, I want you to think of this one as a plane projector. Its whole purpose is to take some random vector and slam it down, forcing it to lie on a specific plane. Now, if you remember only one thing about the vector triple product, let it be this. No matter what your vectors A, B, and C look like, the final answer, the resulting vector you get from A cross B cross C, will always, 100% of the time, lie flat in the same plane defined by B and C. It has no other choice. It's mathematically forced to be there. So, why? Why does that happen? Let's walk through the logic. It's actually pretty cool. Step 1. Look inside the parentheses. You've got B cross C. We already know what that does, right? It creates a new vector, let's call it N for normal, that's perfectly perpendicular to the plane where B and C live. Okay, step 2. We now have to do A cross N. Now, what's the number one rule of cross products? The answer has to be perpendicular to both of the inputs. So our final vector has to be perpendicular to N. But wait a minute, if N is sticking straight out of the plane, what's perpendicular to N? Well, the plane itself. The vector gets shoved right back down into that original plane made by B and C. It's a beautiful piece of logic. Okay, so we know where our final vector is going to live, but how do we actually calculate its components? Well, for that, we turn to one of the most famous and most useful mnemonics in all of vector algebra. All you have to do is remember this one little phrase, BAC minus CAB. Say it a few times, BAC minus CAB. It's super simple, easy to remember, and it is the absolute key to unlocking this calculation without a massive headache. And here's what that looks like as a full-blown identity. Across, B cross C equals B times the scalar you get from A dot C minus C times the scalar you get from A dot B. Now look closely at that result. It's just some amount of vector B minus some amount of vector C. That proves what we just said. The answer has to be in the BC plane, because it's literally built from B and C. That's the BAC CAB rule, doing its magic.
All right, theory is great, but let's get our hands dirty. It's time to put these tools to work with some real numbers and see how this all plays out in a concrete example.
So we're going to be working with these three vectors, P, Q, and R. You can see their components right there. First things first, let's find the volume of the parallelepiped these three vectors create. And for that, we need our volume tool, the scalar triple product. So just like we talked about, we build our 3x3 determinant. We'll put the components of P in the top row, Q in the middle, and R on the bottom. Now we just have to crunch the numbers, and as you can follow along with the calculation on screen, boom, we land on a single scalar value, 14. That's it. The volume of the shape made by these three vectors is exactly 14 cubic units. Next up, let's tackle the vector triple product using our handy BAC CAB rule. So our formula is going to be Q times P dot R minus R times P dot Q. Let's do the easy parts first. Step 1, we need the scalar P dot R. A quick calculation shows that's just 3. Step 2, we need the scalar P dot Q. That comes out to 2. Perfect. Now we just plug those scalars back into the formula. So we get Q times 3 minus R times 2. We do that last bit of vector math, and there's our final answer. The vector 2, 3, 4. Okay, before we wrap up, we have to talk about the biggest, most common pitfall. This is the gotcha that trips up pretty much everyone when they're starting out. And it's this dangerous assumption that cross products behave like the multiplication you learned in grade school. They absolutely do not. This is so important to burn into your memory. A cross, B cross C, is not the same thing as A cross B cross C. In math terms, we say the vector cross product is not associative. You can't just move the parentheses around wherever you feel like it. And here's the proof, plain as day. On the left, that's the problem we just solved, P cross Q cross R. Our answer was the vector 2, 3, 4. Now look at the right. All we did was move the parentheses. We're calculating P cross Q first, and then crossing the result with R. And look what we get. A totally different vector. -12, -3, 15. I mean, they're not even remotely close. This shows you the parentheses are absolutely critical. They control the entire problem. So let's boil this all down. Here are the 3 key takeaways you need to walk away with. Number 1, the scalar triple product is your volume tool. It gives you a single number, a scalar. Number 2, the vector triple product is your plane projector. It gives you a new vector that's guaranteed to be in the same plane as the middle and last vectors. And number 3, the big one, watch out for the gotcha. The cross product is not associative, so the order of operations, defined by those parentheses, is everything. And just like that, vector triple products are demystified. But this leaves us with a really cool idea to think about, right? The vector triple product isn't just a math problem, it's a projection tool. Now that you understand how to force a vector onto a plane, where else can you use that? I mean, think about physics or computer graphics or even robotics. Anywhere that projecting one thing onto another is the key to solving a problem, the applications are really all over the place. Thanks for tuning in.